Okay, so this is question number 1 of the magnetic fields homework booklet. So in question number 1 we have a figure here. It shows a horizontal wire which is held in tension, which basically means that it's kept straight, and it's between two fixed points P and Q. Some of this wire is positioned so that it's between the poles of a magnet, and we've got a north pole and a south pole here. And so there's a uniform horizontal magnetic field at right angles to the wire. So the current's going this way and the magnetic field's going that way. Wires connected to a circuit P and Q allow an electric current to be passed through the wire, as it's shown in the diagram. So part 1, we're asked to state the direction of the force on the wire when there's a direct current from P to Q. So this is an example of Fleming's left-hand rule. We take our hand and we point our second finger, our middle finger, from P to Q. We then turn our hand round so our first finger is facing from north to south, so it's kind of coming out of the paper. And then if you do that, your thumb will be pointing downwards. So the direction of the force is in a downwards direction, and that's worth 1 mark. In a second experiment, instead of having a direct current, an alternating current is passed through the wire. And we're asked to explain why the wire will basically vibrate vertically, why it will move up and down. So if we're going to explain it, we've got to start right at the very beginning, and we've got to say exactly what's going to happen. So we already know that the force is at 90 degrees to both the field and the current, which means the force is vertical. And we saw that before because it was downwards. The magnitude of the force changes as the magnitude of the current changes. So we're basically saying how, when the current changes, how the force changes. And we're basically saying that when the current gets bigger, the force gets bigger, and vice versa. And the force is reversed when the current is reversed. So in other words, if the current's going the opposite way, then the force will go in the opposite way. So if we put all of those things together, because alternating current continuously changes direction, that means that the force must continually also change direction up and down, and so your wire vibrates. So in terms of the 3 marks that we're looking for, basically you're looking for the fact that this happens, and then your second mark is for saying that the magnitude of the force changes, and then your third mark is basically saying that the force is reversed, and so the wire moves up and down because AC continuously changes direction. So your third mark is kind of these two together. And then in part B, we have a permanent magnet that produces a uniform magnetic field, and the flux density of this field is 220 millitesla. The length of the wire is 55 millimeters, and we're asked to show, so we're basically showing that something's true, that the maximum force on the wire is about 40 millinewtons when there's an alternating current of root mean squared value 2.4 amps in it. Well, the maximum force happens when we have maximum current, really. And if we write that down, then we get 1 mark. Now the peak current, when we're looking at alternating current, is simply the root mean squared current multiplied by root 2. Now the root mean squared current is 2.4, so 2.4 times root 2 gives us 3.39 amps. We then take that and substitute into our equation. So this is the equation for a wire in a magnetic field. So the force is equal to magnetic flux density multiplied by the current multiplied by the length of the wire. So we've got magnetic flux density multiplied by the root mean squared value of the current multiplied by the length of the wire. And if we do that, we get 4.1 times 10 to the minus 2 newtons, which is approximately 40 millinewtons. So basically, because we had to show that this is true, we had to show our answer to more significant figures than was given in the question. And if we do that, then we get all 3 marks. You get 1 mark for this part, 1 mark for working out the peak current, and then 1 mark for your final answer. Okay, so in the final part of this question, we are told that we've got the length of the wire, which is from P to Q, is 0.40 meters. And when the wire vibrates, transverse waves are propagated along the wire at a speed of 64 meters per second. So waves travel down this wire at this speed. We're asked to explain why the wire is set into large amplitude vibration when the frequency of this AC supply is 80 Hz. Large amplitude vibration basically means resonance. Now there are 2 ways to do this. We can, the first way is to calculate the wavelength of these waves, because if we can look at the wavelength of these waves, compare it to the wavelength of the string or the wire, if the conditions are right, then resonance will happen. So The wavelength of this wave is just the speed over the frequency. So 64 over 80, so that's 64 meters per second. 80 is the frequency of the supply, which gives you 0.8 meters. If we compare this to the length of our wire, then we can see that the length of the wire is half the wavelength of the wave. So if that happens, and you remember back to your waves, if that means that you basically get just one loop, and so therefore the conditions are right for fundamental vibrations to happen. So therefore, if these conditions are met, which they are, then the wire is going to resonate because you're going to set up a standing wave, which is the fundamental vibration. So therefore, resonance is going to happen. If we're thinking about marking points for this method of doing it, calculating the wavelength is 1 mark, saying that the length of the wire is the wavelength over 2, and so therefore you're going to get a fundamental vibration is the 2nd mark, and then stating that the wire resonates because the wavelength is half the wavelength of the wave is your 3rd mark. So that's the first way of doing it. The second way of doing it is to calculate the natural frequency of the wire. Well, to do this, we need to work out, considering this particular wave, if we want the fundamental vibration, we need to know what the wavelength of the wave is. So for that to happen, if this is going to oscillate at the fundamental vibration, then the wavelength will be twice of this length here. So therefore would be 0.80 meters. So if we then do the speed divided by this wavelength, we end up with 80 hertz. So 80 hertz is the natural frequency that this wire will have in order to vibrate at the fundamental frequency. This matches the frequency of the AC supply, which is your driving frequency, and so therefore your wire resonates. So if you do it this way, you get 1 mark for calculating the natural frequency, you get 1 mark for calculating this wavelength in the first place, and then thirdly, you get a mark for basically saying that the wire resonates. So that was question number 1 of the magnetic field homework booklet.